we've looked at up till now are games where people have been using finite sets of strategies. So the pure strategies have had a finite set, and in more general settings, sometimes it's very useful to have continuum action spaces. So ones where we can actually use calculus to calculate the Nash equilibrium. And so let's take a look at a classic example of that, which is one that has a very important application. So this is a stylized version of a tragedy of the commons. So what are we looking at? We're looking at a society. So think of a society of fishermen. They all have a choice of how much time they want to spend fishing. So in particular, the choice that they're going to have here is an AI which represents the amount of time spent fishing per day. And if we have n fishermen in the society, then the total time spent fishing in the, say, the lake near the society is this A1 plus A2, etc., plus AN. So the sum of all the times that they're spent is how much aggregate time there is per day fishing. So we think of this as a choice that they're going to make over how much time they spend on average per day fishing. Now, when we think about the payoffs then, so we've got these n fishermen, they're each choosing a time per day, and we begin to think about how we're going to model payoffs. There's sort of two effects of how much time you spend. So one effect is that you catch more of the available stock of fish. The other effect is the more fish you take out of the lake, the slower they reproduce, and you deplete the stock of fish over time. Okay, so let's think of a world where we've got 1,000, so we're going to normalize the payoffs here, and we choose the stock over time is just going to be represented by a function, and this is just an example of a function that could work, but let's say it's 1,000 minus the sum of the AIs of each of the individuals, and so let's think of the situation where we'll put some limits on what the available AIs are, but the stock is going to be given by a function which is decreasing in the total amount of time that all the fishermen spend. Fisherman J, a particular fisherman, what is their catch? Their catch is the amount that they fish times the total stock that's available. So they're spending a certain amount of time, and the amount of fish they catch is proportional to their time times the size of the stock of fish that's there. So there's an effect that they catch more as they fish more, but the more that's being fished, the lower the stock is that's available, and so we're seeing a trade-off here. Okay, so now let's look at trying to calculate what the best responses are in this game. So when we look at the best response of a given fisherman, what do they want to do? A given fisherman is trying to maximize their overall payoff. There should be an extra parenthesis here. So what are they looking at? They're maximizing the amount of time they spend times the stock. So this is, remember, how many fish they catch. And so when we look at that in detail, it's AI times 1,000 minus AI plus sum of AJ's for J not equal to I. So this is the total amount of time that's spent fishing by all the fishermen. This is the total stock that's available, and then this is the catch that the given individual is going to get per day if they're fishing that much. Okay, so this is now a simple maximization problem. We can go ahead and just solve this by calculus. So we take the derivative of this, we set the derivative equal to 0, and that'll give us a necessary condition for a strategy to be a maximizer of this function. So if we're trying to maximize this with respect to the AI, we take the derivative of this whole function and set it equal to 0. The derivative of this function is just this. It's 1,000 minus 2 times AI minus the sum of the j's not equal to I, AJ, and we set that equal to 0 to find the optimal AI. Okay, so this is just a simple calculus problem. We're assuming that you are familiar with taking derivatives. So here we're just taking a derivative, setting it equal to 0, and that's going to have to be a condition for an AI to be a maximizer. Okay, so if you solve that, then solving it for AI, what's the best response of AI in this game? Well, you look at solving this. When we solve this equation, You can solve that directly. You get AI is equal to 500 minus the sum of the AJ's not equal to I over 2. So you're basically taking the actions of the other players, subtracting those off from 500, and that gives you an optimal AI. Okay, so now let's try and solve this. So that gives us a condition for what each best response is as a function of the other player's strategies. Okay, so we've got our optimal best response for I as a function of the other player's actions, and now we're solving this supposing that every player is playing the same action. So in a symmetric game, let's look for a symmetric equilibrium, a point where everybody's doing the same thing. So if we suppose that every AI is equal to some A star, then if we plug that into the equation here, what do we end up with? We end up with this equation that A star has to satisfy. A star is equal to 500 minus n minus 1. That's the number of other players besides I, right? That becomes this. Times AI star over 2. And if you solve that, that's just a simple equation. We end up with A star is equal to 1,000 over n plus 1. Okay, so that tells us that each fisherman is going to look at, spend a certain amount of time. The time is 1,000 divided by n plus 1. So for instance, if you have 10 fishermen, then you spend 1,000 over 11. If you have 100 fishermen, then you're spending 1,000 over 100 plus 1. So the larger the number of fishermen available, each one's going to fish a little bit less. But this gives us an equilibrium, a symmetric equilibrium, Nash equilibrium of this game. Okay, so we have the Nash equilibrium action, the symmetric Nash equilibrium action of 1,000 over n plus 1 for each fisherman. So when we look at the total catch then for a fisherman, they're each fishing the 1,000 over n plus 1, and then that is times the stock here of 1,000 minus the total number of fishermen times how much each fisherman is fishing. So when we look at the stock, we're going to get 1,000 minus n times 1,000 over n plus 1, or this is equal to 1,000 over n plus 1. So when we multiply this times the stock, we end up with 1,000 over n plus 1 squared. Okay, so we have a prediction for what the catch of a fisherman is going to be under the Nash equilibrium. And now what we can do is compare that to what would happen if instead the fishermen got together and coordinated and tried to put a catch limit on fish. So if they tried to optimize jointly instead of separately, what would happen? So let's take a look at that. So in particular, if we want to solve for the optimal limit, what we can do is maximize the total catch for the whole society. So we'll maximize the total catch of all fishermen, which is going to be how much they fish in total times the total stock. So for maximizing that, what are we doing? We're maximizing the sum of the AIs times 1,000 minus the sum of the AIs squared. So if we try and maximize this, we take the derivative. What do we get? We get 1,000 minus 2 sum of the AIs is equal to 0, or the solution to that then is the sum of the AIs is equal to 500. So if we're in a symmetric situation, if we give the same allocation of fishing rights to each fisherman, then that means that AI is going to be 500 over n in an optimal total maximizing solution. So now we can go back. What's the total catch per fisherman in this situation where we're optimizing jointly? Well, they're each fishing 500 over n. The total catch then is 1,000. The stock is 1,000 minus n times, this is the n times 500 over n, or 500. So we get 500 squared over n as the total catch per player. Okay, so with those two in hand,
Now we can compare what the optimal is in terms of joint maximization, 500 squared over n. What's the Nash equilibrium catch per capita? Instead, that's 1,000 squared over n plus 1 squared. So for instance, if we had a population of 1,000 fishermen, the optimal catch, the 500 squared over n, would be 250. But if we had 1,000 fishermen, the Nash catch of 1,000 squared over 1,001 squared is actually less than 1, just less than 1. So here we see an enormous difference between what we would get in an optimal society where we regulated fishing and one where everybody was left to maximize on their own. And obviously this gives us some insights into why there's a tragedy of the commons, why people overfish, why we end up with extinction. It helps us understand things like the disappearance of the buffalo in the American West in the 19th century, why we have problems with fish disappearing in open waters, international waters today. So the game theory can give us some insights into the differences between what a society would like to do and what it would do if left to its own.